So today we will continue with the Rham cohomology, and in particular we compute the Rham cohomology of the spheres. Before that, let me recall what is a deformation retract. So if you have a submanifold and you take I, the immersion map, so just the identity map restricted to S, we say that S is a deformation retract. Deformation retract of M if there exists a map from M to S, smooth, such that F composed I, so this is a map from S to S, is the identity on S. And I composed F, this is a map from M to M, is homotopic to the identity on M. Okay. So this is similar to saying that you can take the space M and squeeze it on S and squeeze it continuously, because this homotopy gives you basically a path for every point. In your manifold, you have a path that goes to S. Okay, this is very simple. This, for instance, is always possible if you have a connected space. Yeah, you can just take a path. But the nice thing here is that everything is nicely and well continuous, also with respect to M. And we saw before that if you have two maps which are homotopic to each other, then the map induced in cohomology is the same. So as a corollary, you get that is S is a deformation retract. So of course, the corollary of not of this definition, but of the fact that maps, homotopic maps give the same mapping cohomology, you get these are isomorphic. And this isomorphism is given exactly by this I in one direction and F in the other direction. I star, sorry, and F star, of course. Okay. So now with this in mind, we have some tools to compute cohomologies. And our example for today will be to compute the Rham cohomology of spheres, n spheres. So n-dimensional spheres. So Sm is the sphere in Rm plus 1. And we take n the north pole of the sphere, so just the point 1 and then all zeros, and s the south pole, so -1 and then all zeros. Okay. And then we take u to be the sphere minus the north pole, and v to be the sphere minus the south pole. And the thing that we observe is that u union v is everything. And u and v are diffeomorphic to each other, and in particular, diffeomorphic to Rm. So this is a known fact. The sphere minus a point is diffeomorphic to Rn. And in particular, this implies the second part, the Rham cohomology of U by the Poincaré lemma, which we saw yesterday, is trivial. Yeah, so you have one connected component, so R, but otherwise you're star-like, so you're 0. And now actually with this deformation retract thing, we know something better. You need something less than star-like, which is simply what you call it, contractible. Yeah? contractible automatically gives you this as well because of this corollary. And one other thing that we know is the U intersected V, which is just SM minus North Pole, South Pole, admits its equator as a deformation retract. So if you think about it in the regular S2, if you take away the top point and the bottom point, you can squeeze everything to the equator, which in this case is a S1. But in general, and this equator, so U intersected V is homotopic equivalent. That's how we write homotopic equivalent to SM minus 1.
Yeah, but 1 second. Is U intersected V one line up Sn minus 2 points, or is it?
Yeah.
But I thought if we just remove those 2 points, it's Sn minus 1 with. I'm sorry, that was that was stupid. No, it's okay.
Okay.
Yeah.
I mean, if you remove 1 point, you have what, Rm by
Yeah.
the stereographic projection, then you remove 1 more point, and then you can retract this on unitary things, right?
Yeah. No, I just had a brain fart. It's good.
Okay, so now we have some prime candidates to use Mayer-Vittoris. Yeah. So Mayer-Vittoris gives us long exact sequence in cohomology. Actually, I'm going to do it on the next slide. Okay, so Mayer-Vittoris. Okay, so now we get this long exact sequence in cohomology, the Rham P of U plus the Rham P of V, and this we know is 0 unless P is equal to 0. And this goes into the Rham of the intersection, which we know is the same as the Rham of SM minus 1. You have the whole space SM, and then again you go here. And then you continue. Now the thing is, if P is at least 1, so if P is non-zero, so for P greater or equal than 1, and also M greater or equal than 1, these are 0 and these are 0. And we know that when we have an exact sequence with 0 here and 0 here, then these two must be isomorphic. Yeah. So this is this here, and here we're using the fact that U intersected V is homotopic equivalent to SM minus 1. Okay. So that's pretty nice, because it means that we can simultaneously lower or rise the indices, and these are all equivalent. So if you want to think that here we have some kind of tab where you have M equals 0, 1, 2, here you have P equals 0, 1, 2. Okay, this is nothing but 0. So this is okay, this is nothing, sorry, it's nothing. It was just M where M is, but this is 0, 0. So here we'll have something we don't know, but whatever it's here is the same on this all diagonal. Yeah. And this is true for all diagonals. This is true here, this is true here, this is true here, etc., etc. So what we really need to do if we want to determine this spaces is determine what is happening here. Yeah, but one of the two numbers is 0 and the other one is non-zero. And then all the information is transposed. So let's see what happens when m is equal to 1. So for m equal 1 and p equals 0. Okay, here you have the 0 cohomology of S1. Sorry, this is a 0. Here you have U, 0 V. You have the Rham 0 U intersected V. This goes into the Rham 1 S1. And here we go. This should be the sum of H1 of U and H1 of V, but those are contractible, so we have 0 again. Okay. And also we know that we don't need to go any further because the highest dimension here we have for S is 1. So H2 is going to be 0. Okay, so we know. And okay, so let's compute this. Well, this is isomorphic to R because it's just the number of connected components. This is R2 because these are connected to, I mean, this is one connected component. This is one connected component. This intersection has two connected components. Yeah. Because this is the U and V's in S1. So again, we have R plus R. And this one is the one we don't know, but it's the one we care about. And yeah, here you can see just by counting dimensions, basically, that H, the R1 of S1 is isomorphic to R. There is maybe a more, let's say, more systematic way to do this, which is the so-called rank formula, which tells you that when these are vector spaces, you like if the sum with signs, so 1 minus 2 plus 2 minus whatever it's 0 must be 0. But otherwise, we can really do it by hand. So maybe let's do it just once. Okay, so this must be injective. So here, the image has dimension 1. Yeah, inside here. So the kernel of this map has also dimension 1. The kernel of this map has dimension 1. So the image again has dimension 1. So the kernel has dimension 1. So the image must have dimension 1, and it must be surjective. So this is dimension 1. Therefore, it's isomorphic to R. Okay. And we know otherwise that for P greater than 1, as I was saying before, this is trivial for dimensional reasons. Yeah? Okay, so let me draw this thing again. So here we're trying to compute the Rham cohomology of Sm. Here we have P equals 0, 1, 2, 3. And here we have M equals 0, 1, 2, 3. Okay, 0, 0, it's easy. It's the number of connected components in S0. And by the way we defined S0, this is actually 2 points, 1 and minus 1. So this is R2. And remember that this thing I said that you can, lower indices and the old diagonal is the same. It's only true from here. So it's not true here. So these are not all R2s. In fact, we saw the 1, 1 is R. So this is what we just saw. And we also saw that for P greater than 1, these are zeros. All of these are zeros. Yeah. And one other thing that we know is that each sphere, besides the S0 sphere, has exactly one connected component. So also here we get R's. Okay. And again, we cannot use this fact yet because here p is equal to 0. Well, this is only true for p greater than 1. Okay. So let's see what else we get. So here we get r's on this diagonal because of this and this. So we can higher lower the indexes. Well, here we get zeros for dimensional reasons. This is all zero. So diagonal is r's, and the, let's say the upper part is 0 for dimensional reasons. So what we're missing still is what happens here. So we need what happens for 1 less than p less than m. And I'm sorry, I need to get this boy out of the way. Okay, so let's see what happens. Okay. So again, using this formula, we see that we don't really need to check all possible combinations of p and m satisfying this, but it is enough to find h1 of Sm for m greater or equal than 2. Yeah, you see, because here we have p equal 1 and m greater than 2. So this is this first spot, but then it's also all the other m's. So you get the first column. Let's say the column with p equal 1, you get all of it, and then you can use this formula and transpose everything. Okay, so how do we do this? Well, again, of course, my Vitoris. So we have 0 going to h0 the Rham of Sm, h0 of u plus h0 of v. And here you have h0 of u intersected v. And here we finally go what we care about, which is the Rham of Sm. And then we know that the next step is 0 because again, it would be h1 of u plus h1 of v, but we know that those are 0. Okay. And okay, so let's see what this are isomorphic to. This is just one connected component because remember we're taking greater or equal than 2. So this is just R. This is one connected component, one connected component. So here we have R2. And here again, now for m greater than 2, this is only one connected component. So it's not R plus R like we had before, but it's just R. Mm-hmm. And now again, so what happens to this? We can do it again slowly. So you have that this map is injective. So the image has dimension 1 here. So the kernel of this map has dimension 1. Therefore, its image has dimension 1. Therefore, it's surjective. So everything goes to the kernel, but this also must be surjective. So the Rham cohomology of order 1 of Sm is 0. Okay. So this gives us the theorem, which we just proved. The Rham cohomology of the sphere Sm is 0 if p is different than m and they're both positive, strictly positive. It's R if they're the same and positive. It's R2 when they're both 0. And it's R when p is equal to 0 and for any m, which is non-zero. Okay. So the way we showed this theorem actually gives us something a bit more general, is that if m is compact and connected, the Rham cohomology of degree p is always finite dimensional for every p in n. And the idea of the proof think the details are very easy to fill in. You find a finite cover uj in j of m. Okay, finite is not a problem because it's compact, such that any size intersection is contractible or empty. So finding such a cover is maybe the more delicate part, but it is possible. And then use Mayer indicatores inductively on the size of J, on cardinality of J. Yeah, because basically you get lots of zeros because these intersections are empty in this exact sequence. So you always get down to some finite number of generators. Now let's see an example when that is not the case. Take M to be R2 minus the natural, minus the natural numbers on the first axis. So minus n times 0. Okay, we're just removing points, infinitely many, countably many points. So first of all, observe that M is not compact. So we cannot apply what we said before. And what I want to do now is show that actually the first cohomology group, it's infinite dimensional. And for each M in N, we take rho M, theta M, polar coordinates. Centered at the hull. Yeah, so you have this hull, M0, and we take polar coordinates there. So we know this describes the whole space, but we also know that if you think theta as a function, this is not continuous. Yeah? So theta M is not smooth, but its differential is well defined. Smooth 1,4, which is closed, but not exact. So this is something you should have seen in your complex analysis courses. Okay. Yeah. So what I'm claiming is that d theta m is a non-zero element of the Rham cohomology of M. Okay. And I want to show they are linearly independent. Okay. So consider CM, the circle, the circumference of center M0 and radius, let's say 1/2. And take IM to be the immersion. Okay. Then when you integrate this form along this CM, which okay, technically you can do, you always have to put this I star before. what you get is 2 pi times delta IM. Meaning that if you take the integral over the correct whole, you get 2 pi. And if you take the integral over the wrong whole, then you get 0. Okay? But this immediately proves they're linear independent. Because, yeah, assume not independent, then we can write, let's say, 0 as a linear combination, no? So sum of AI d theta I. Oh, maybe I use J, AJ theta J. And okay, technically this is, we're all talking about the Rham classes, yeah, because we have to show that they're independent in the Rham classes. But the thing is that we know that the integral does not depend on the representative. This is something that we saw. So in particular, if you integrate, 0 is equal to the sum of AJ integral over CM. So we fix one CM and d theta J. But now this is precisely 2 pi AM. Yeah. So this implies that AM is equal to 0 for every M. Therefore, they're linear independent. Okay. So this is a way in which integrals and forms relate to each other. There is actually, in particular on compact manifolds, there is a very strong, well-known theorem, which is the Poincaré duality on compact manifolds. So we will only deal with compact manifolds here. There is a more general version of this Poincaré duality, which does not require the manifolds to be compact, but we'll stick with this. So we take M, be a compact oriented manifold. So not just orientable, but oriented, in the sense that we picked an orientation. So dimension N. And then we have the linear operator, which is the integration. We have the linear operator, integral over M, we call it, which goes from the nth cohomology group into R, and it takes a class, and it sends it to its integral. Yeah, we already showed that this is well defined. It's independent of the representative of the class. It's linear and blah, blah, blah. But we can do something a bit more general. So of course, we can think general. We can think of the integration. So we know what is to integrate over M. You need to integrate on top degree forms. Yeah, you need to integrate something which is the same dimension of M. And another way to obtain something which is of degree M is by taking the wedge product of two smaller things. So we still call it integration over M, but now we're thinking of HQ times Hn minus Q into R. And we take two forms, omega and omega prime, and we send it to the integral over M of omega wedge omega prime. But this is again well defined. Because first of all, this is an N form, and if you change the representative here, the integral stays the same. This is also something that we checked already. And the theorem, which is the Poincaré duality, which we will not prove, is that if M is, again, compact, oriented, dimension M, dimension of M equal N, and if you take Q between 0 and N, then this map, this integral map, is a non-degenerate bilinear form. Okay. Hence, in addition, this is a thing in general. If you have a non-degenerate bilinear form, then you automatically have that here one is a dual of the other. And for finite dimensional spaces like we have in this case, this is actually not hard to prove. Okay. So these are all finite dimensional spaces. So non-degenerate bilinear form, you can just think that it means that it's a bilinear form, so it's represented by a matrix. Yeah. So you're asking that this matrix is positive definite. Sorry, yes, no zero eigenvalues, not positive. Yeah. And yeah, and anything like this always gives you this duality. And the duality is given, I think you know, no? No, maybe. So maybe I'll explicitate this duality. So let's say the map that goes from here to the dual here. You take a form omega and you send it. So I have to give you an application which takes the form omega prime, send it to the integral of Rham of omega, which omega prime. Yeah. So this is the map that gives you this isomorphism. And here, instead of this integral, you can put the bilinear form. Every time you have a non-degenerate bilinear form, you put that non-degenerate bilinear form, and that works. Okay. But one thing that we saw where we used integrals is to not only integrate over the manifold M, but also how to integrate on submanifold. So given a compact oriented submanifold of dimension k, in a compact oriented submanifold, of dimension n. So what I'm saying here is that S is compact oriented, and is of dimension k, and it's a submanifold of M, which is itself compact oriented at dimension n. And we take the immersion I west to M. We have another linear map. Linear map that goes from the kth cohomology of M into R, which takes omega and sends it to the integral over S of I star of omega, right? This is something we've seen when we define the integration. This is basically thinking that you're restricting this omega to S, and then since these are of the same degree, you can take this integral. But now we have a linear map from HKR. So this is, it is an element of HK, the Rham star, right? This is the definition of star, of the dual. And so by Poincaré, duality, there exists a class which we call eta S, which is in the n minus k cohomology group, such that if you take this integral I star omega This is the same as taking the integral of Rham of omega wedge das for every omega class. Yeah. So you can see as integrating along a submanifold is the same as integrating against what is called a weight sometimes. You might have seen this where you did L2 spaces in some functional analysis. Usually the weights there were something that kind of cut tails or something like this. Your weights represent more the fact that we're integrating on a submanifold. And this eta S is the Poincaré dual class of S. And this whole thing can be tried for non-compact manifolds, but there things don't work really well because when you, first of all, when you cannot just take this integral, you need forms with compact support, otherwise you could get infinity. But then when you do this thing here, at least one of the sides must have compact support. So the dual of the one with compact support is the one without compact support, and vice versa. And so yeah, things change a bit because then when you take the dual of the things with compact support, you could not really talk about smooth forms anymore. You have to talk about basically forms which have distributions as coefficients. These are called currents, and it's a whole new topic, which is very much studied. It's very active field. And in particular, I mean, you know, the distributions in, let's say, in analysis are used very much to study behavior of differential equations. Because like in principle, you don't know that a smooth solution exists. So you come up with this distributions, whatever they are, and then you hope to show that in fact, this is a smooth map or C0 or L2, whatever you can prove. And this is actually very much done the same, but with forms. So it is more geometric interpretation of these objects. Okay, this actually concludes chapter 3, which was cohomological complexes and the Rham cohomology in particular. And now it is time to move to sheaves. But before we can actually move to sheaves, we have at least a week of just ring algebra. So algebra, just commutative algebra. So chapter 4, sheaves, which will include check homology. But first of all, we have to do some commutative algebra, where some means a lot. Okay, so forever, for the rest of times, R will be a commutative ring with unity. So it's a ring, it has an addition, it has a multiplication, and there does exist a unity with respect to this multiplication. And a module A over R, sometimes also called the R module, is an abelian group, A plus. So A is the object, plus is the operation, which also has another operation, has an operation which goes from R times A into A, such that R of Sm is the same as Rs times M. So this is for R and S in R and M in A. So some kind of associativity. Then you have distribution property. Everything above still stands, yeah. So R is still in R and small m is still in A. And now introduces n in A. And also distribution in the other direction. So R plus f from m is Rm plus Sm. And then you have this unity, which 1 times m is equal m, where by 1, I mean the unity in R. Yeah. So this I have to write because, yeah, I mean, this is true if we had 1 times R, this is equal R because 1 is the unit in R, but it's also true in A. Some examples. All abelian groups are Z modules. Vector spaces are modules over their field. If you have a vector space over R, this is a R module. And if you have a ring and an ideal inside ring, then this ideal is R module as well. Yeah. And definition is that a ring R is Noetherian after ambinoether if its ideals are finitely generated as R modules. Okay, I didn't tell you what finally generated means though. So maybe let me tell you what finally generated means. Into def. A is finitely generated if there exists phi from R, sorry, R not real numbers, but R the ring, k times into A, surjective morphism. Okay. And a morphism of rings is simply something which preserves all these properties. And another definition is the one of free module. So A is free of rank K if it's isomorphic. This is a module isomorphism to the sum. Okay. An example, which is maybe more relevant to us and perhaps you've never seen, I hope, is that if you have a complex manifold and a holomorphic vector bundle, on M of rank K. If we take an open subset, then the space of a holomorphic function is a ring. Particularly, it's an abelian ring with unity. So what we like as rings in this section. And the space of sections from U to E is a module over this ring. Yeah, if you have a section and you multiply it times a function, this is still a section. And in particular, if U is trivializing for E, then this is free. Of rank. Okay. Simply because you can think that this E is just C to the K, and so you need different coordinate functions, and simply each coordinate, it's an element of OMU, so it's just OMU to the K. Definition. An R submodule of A is a subgroup such that RB is in B whenever R is in R and B is in B. So what do you expect? A definition, given a family AJ, J and J of R modules, the direct sum, which we denote like this, is the submodule of the infinite product given by elements AJ. So with this, I denote an element in here, yeah, such that AJ is equal to 0 for all but finitely many. J is in J. Yeah. Some quick observation: if you have a morphism between modules, then both the kernel, the image, are submodules. And if B is a submodule, so no, it's not this one, it's just other B and A's, then also A mod B. So this is the group quotient. This is also module. Okay. So now that we have all these objects, we can also define exact sequences. So we have kernels, we have images. So we want to define exact sequences. So we take A, B, C are modules, modules, alpha from A to B, B beta from B to C, morphisms, and we say that A, B, no, sorry, beta is exact if the kernel of beta is the image of alpha. Okay, usual. And while 0, A, alpha, B, beta, C, 0 is a short exact sequence if, okay, usual, alpha is injective, beta is surjective, and then ABC is exact. Yeah, so usual things. But now we have something a bit more interesting, which didn't really happen for vector spaces, which is splitting. So a short, exact sequence of R modules splits if there exists a morphism from B to A such that F composed alpha is the identity on A. So it's basically asking that there exists a partial inverse. And lemma, the following are equivalent. I don't know if you're familiar with TFAE. The following are equivalent. 1. The sequence splits. 2. There exists a G from C to B such that data composed G is the identity on C. So it's kind of this other inverse. So having this inverse is equivalent to having this inverse. Or, and this is perhaps the most illuminating one, there exists an isomorphism between B and the Dirac sum. Which makes the diagram commute. And here we have identity maps, identity, and identity. Here we have this phi that we ask the existence of. And here the maps, one is just the immersion in the first factor, and the second one is the projection to the second factor. Okay. Okay, let's go on with the proof of this fact. Okay, if we have 3, which was this one, of course you have both 1 and 2. Okay, because you can just take this F to be phi composed projection to the first factor. Yeah. And you can take G, sorry, F goes from B to A. Yeah. So phi composed projection to the first factor, and G goes from C to B. So you take this, and then you send it to 0, comma C. Okay. So 3 implies 1 and 2. Now we will show the 1 implies 2. And we will skip, or let's say leave as exercise that 2 implies 1. And then we will show that 1 and 2 together imply 3. So this is a constructive proof. So we know that it splits, and we have to prove that it kind of splits in the other side. And we define F prime to be the identity over B minus alpha composed F. Now this is a map from B to B. Now let's look at it again. So identity minus alpha composed F, and F is this map that goes back. So what happens if you combine F prime with alpha? So this is a map now from A to B. Well, here you get alpha, and here you get alpha composed F composed alpha. But these two together are the identity on A, because the F is the one that gives us the splitting. In particular, this is alpha minus alpha, so this is 0. What does it mean? Well, this means that the image of alpha is contained in the kernel of this F prime. And actually, I want to prove that they're the same. So vice versa. If I have an element in the kernel of f prime, then 0 is f prime of v. But f prime of v is also v minus a of f of v, right? Just by the definition of f prime. But then v is alpha of f of v, so v is in the image of alpha. Particular kernel of f prime is the same as image of alpha. And since the sequence is exact, this is also equal to the kernel of beta. Yeah. So now we pre-compose with alpha. What happens if instead we post-compose with beta? So also beta compose f prime, it's going to be beta, yeah, simple by definition, minus beta composed alpha composed f. But beta composed alpha, again, because the sequence is exact, is 0. So this is simply beta. Okay. What does it mean? Well, this means that beta is injective and surjective on the image of f prime. Just on the image, because you have this. But then this means that beta admits an inverse if you restrict it to image of f prime. So we define G as the inverse of beta. And of course, this now does what we want it to do, because yeah, this is what we were asking, that basically G was the inverse of beta. Yeah. And of course, we have to, I mean, the reason why we had to use all these image things, where is it? Okay. Yeah, is that I got lost. Yeah, this is defined on C. And oh yeah, sorry, and beta is surjective. That's important. Okay, exercise is 2 implies 1. You do it in a very similar way. You have to define some kind of supporting function and show something like this. But then the 1 plus 2 implies 3. So 1, I mean, assuming either 1 or 2, we see that they're equivalent. We can take phi to be just f plus beta. Yeah, so you have to define this phi as a map from B into the sum A plus C. And yeah, you simply send in the 2 factors separately, and here you have to use this kind of inverse, which is the f that gives splitting, and here you just use beta. Okay, and the diagram commutes exactly because you have this condition and this condition. Okay. Okay. The question is, when does something split? When does it not split? Because for vector spaces, this doesn't happen. Exact sequences of vector spaces, they always split. But for rings, this is not always the case. So let's just give a general proposition that tells you that there is some case where it just always splits. So we take a short exact sequence, and if C is free, so meaning it's just the product of R with itself a few times, then the sequence splits. sequence splits. Okay, and the proof is actually not too hard. We will use the part 2 of the previous proposition. So we take generators, free generators of C. The word free here is to mean that they don't have relationship between them. They're completely independent of each other. You can think of them as, if you think of C as R to the K, then this one is 1, 0, 0, 0, then it's 0, 1, 0, 0, 0, etc., etc. And the sequence is exact, so beta is surjective. Therefore, there must be some elements which map to this basis thing. And now, well, we know that we have to define G as some kind of inverse to this beta. And well, this is very easy now. Because you send Vj to Bj. And then extend by R linearity. There is no relationship between these Vj's, so you can simply send each one of them wherever you want and just say, and then extend by linearity. Okay. There are other constructions we can have about modules. So if you take A and B are modules, then we have the group of homomorphism. Then the group homomorphisms over R from A to B of R morphisms is itself R module. No? And in particular, we have induced maps. So if we have alpha from A to B morphism, and C is another R module, alpha induces the map from homomorphism from C to A into homomorphisms from C to B, which simply takes an F and sends it to alpha composed F. Yeah. And so, yeah, I mean, by pre-composition, it does something, but also, by post-composition, it induces something, but also by pre-composition, it does something, but now the arrows are reversed. Yeah. So this is very much looking like a pullback. This is more like a pullback, right? There's also pullbacks basically like this. And the other one is not. There are a few facts about this functor, which is the homomorphic functor, which I'm just going to state. Some of them are easy, some of them are not so trivial, but I'm just going to give it as a list. First of all, if you take homomorphism from R itself into A, this is the same as A. You just take phi and you send it to phi of 1. Yeah? Then you also have this kind of distributive property. So A plus B into C is the same as A into C plus B into C. And you also have it on the second factor. And then you have something about exactness. So if 0 goes to A, goes to B, goes to C, is exact. So notice this is not a short exact sequence, yeah, because we're missing the 0. Then the associated one is exact. Where D is just another one. Exact. And if A, B, C, 0 is exact, so again, not a short exact sequence because we're missing the 0 here, then 0. So when we reverse the arrows, so when we put D on the right, this is what's exact. These two properties together are usually referred to as the functor hom being left exact. Exercise. So when D is a free module, then hom or D dot is an exact functor. Exact functor meaning that it sends exact sequences into exact sequences. Okay. Okay. Another proposition about exact sequences. Sorry, not proof, but prop. If we have a sequence that is splitting, so we can just write it directly as something that's splitted. Splitting. Then 0 hom C D hom A plus C D hom C D into 0 is exact. So the functor, so here we're not assuming that D is a free module anymore. We're just saying that the functor hom takes splitting sequences into exact sequences. Yeah. So let's prove it. We take alpha. It's simply the injection. So A goes to A0. And we know by, I mean, we didn't prove it, but from the list of facts up to the last factor, we know that we have an exact sequence, yeah? Up to here, we know we have an exact. So we only need to prove that this last map is surjective. So we only have to prove that the last map is surjective. Okay, how is defined this map? So this is the map from A plus C D into hom A D. And what does it do? Well, it takes a map F and it sends it to F composed alpha. Yeah, this is how it's defined. No, it's easy because take a map in here. So we have to show surjectiveness. So I have to find the map here, which goes here. Define F of A C, and you see this is where this fact that it's splitting comes in. Simply define it as G of A. And of course, I mean, this satisfies that if you take F composed alpha, this is exactly G. No? See it maybe. Because F composed alpha of A, this is F of A0, which is G of A. Okay. Okay, so now we saw that if you take an exact sequence up to some point, so an exact sequence of without the final part, then you get again something exact. We saw that if D is a free module, then this is an exact factor. So it's an exact sequences to exact sequences. If you take a splitting sequence, this is always going to an exact sequence. So maybe we're kind of dubious and we start thinking that, oh, maybe this is an exact functor. So to show this is not the case, that homomorphism is not an exact functor, let's do an example. So is not an exact functor. Okay, the ring of choice will be the ring of polynomials over C. And the sequence will be the sequence that takes a polynomial, sends it to the polynomials times Z. And here you have to just put the projection, which sends polynomial to this ring, which is just a quotient ring. Okay. And now we can think of CZ as a module over itself, so as a CZ module. Okay. So we apply. What I want to do is apply to this sequence homomorphism over this ring into this ring. Okay. And what do we get? Well, we get 0 goes into hom of CZ modulus CZ times Z. We have to reverse the arrows into CZ. And now this goes into hom from CZ into CZ. And this one goes into hom. Maybe I'll take a bit more space. Hom from, oh, just CZ into CZ again. Okay. And this part we know is exact. What we do not know whether is if this part is exact. So is this one true or not? And the claim here is that it's not. The last morph is not surjective. And why is that? Let's say that we call this map B. What does B do? Well, if you take B of H, so this should be a morphism. So H is a morphism from polynomials to polynomials. And now I have to give you another morphism polynomial to polynomials. So this is a polynomial itself. This is going to be Z times H of Z. Okay. So this is not surjective because basically the image is the ideal generated by Z. Like everything gets multiplied by Z. So for instance, you don't get the constants. But one thing we can observe. Okay, so this proves, let's say, the counterexample. So this functor is not always exact. But we do observe that this map B is injective. You can just divide formally by Z. And Injective basically means that this thing here must be 0. Yeah, because if this map is injective, here the kernel is equal to 0, so the image was equal to 0. But this map was injective, so this must be 0 as well. This is maybe not too surprising, because if you think of CZ divided CZ times Z, this is basically C. C like complex numbers. And that's not, I mean, it's not exactly, because then you have this structure of a ring over CZ, which doesn't come for free in C, right? You have to put it, it's third division. But yeah, if you think of like maps from C to CZ, which are somewhat CZ linear, it's like, oof, not sure if I can come up with something. And in fact, the thing is that you cannot. Okay. Just one more thing, which is tensor products. And then I'll let you go for today. Okay, again, we have A, B, and C, our modules, and map F from A plus B into C is our bilinear. If it is an homomorphism of abelian groups, so which is our linear in each factor, Okay, so you know, remember this. And if you take the group, is also our module. This is also our module. And you know that normally when we bilinear maps, you always think of the tensor product. In fact, what we're trying to define here is this tensor product. And here, more than let's say defining a tensor product, we show by this proposition that there exists only one ring, which should be the tensor product. Sorry, one module, which should be the correct one. So then there exists a pair, A tensor B over R theta, where, so for now, this is just a symbol, where A tensor B is our module. Theta is a map from A plus B into A tensor B. And this is our bilinear, such that for every C, our module, and every map from A plus B into C, which is our bilinear, there exists a unique way to factorize it. So F prime from A tensor B into C morphism of our modules, such that F is F prime compose theta. Okay. So maybe observe that this is the same as saying that the set of bilinear maps from A plus B into C is isomorphic to the homomorphism from A tensor B into C. Okay, this is the same because the map is unique. And the other direction is obvious. And furthermore, A tensor B, theta is unique. up to isomorphisms. Okay. And here the proof, it's constructive and interesting, I would say. It's a nice proof. And it's not too long. So let's have a look. So we define T to be the free module generated by elements of the form AB with A in A and B in B. Okay, so this, you think of this as a basis, like this A and B are a basis. So you're kind of forgetting that there is relationship in A and relationships in B. Okay, this T is not the sum of A plus B. It's just generated by all possible pairs. And then we take Z, be the submodule generated by elements of the form, and here there is a list, and it's basically a list that guarantees bilinearity. Yeah. So this is, I mean, once you quotient this out, what you're telling is yes, okay, we do identify actually things according to the relationship. Okay. And in fact, we define A tensor B to be T mod Z. And denote A tensor B for the equivalence class of the pair AB. No? Equivalence class mod Z. And now we have a few things. For instance, the morphism that sends a pair. So now we're really in A plus B. We're not in this abstract T anymore. Into the tensor product. This is sum, this is the tensor. Takes A, B and send it to A tensor B. Well, this is bilinear. So what we wanted now. And if F is any bilinear map, any bilinear map, we can extend it to a map from T to C by R linearity. No? Because remember, basically the elements of A plus B are just the free generators of T, so we can just say linearity. And then since F is bilinear, it actually descends to the quotient. So if you restrict it to Z, you get 0. And F prime of R defined as F of R is well defined. Well defined on T mod Z. Okay. Um, The only thing left to prove is uniqueness. It is an exercise, which of course you should try to do using this kind of universal property. Yes. And I'm going to give just the last list of properties for this. So properties. If you take the tensor product with the ring itself, you get A. The map here is simple, just A times R goes into RA. A times B is the same as B times A. And you also have associativity. So A times B times C is the same as A times B times C. And then you also have distributivity with respect to the sum. Yeah. And this looks easy. And in fact, these are very true and easy for vector spaces. But for modules, you have to be a bit more careful. You really have to use the universal property. Okay. One last observation is that the homomorphisms from A tensor B into C, so this is all bilinear maps from A plus B into C. This is isomorphic to homomorphisms from A into homomorphisms from B to C. So basically here you take a map, which is like A tensor B goes to F of AB. And you send it to a map, which takes A and sends it to the map that takes B and sends it to FAB. It's a bit maps sending maps into maps. It's a bit hard to write. Here, square parenthesis makes it easier to read. Okay. So this is just some properties of the tensor product, which we were familiar with for vector spaces. And what we're saying here is they also hold for modules. But in a non-trivial way, because you really need to use this universal property. Yeah? And in fact, even the construction of this tensor product is more interesting than the one you do for vector spaces. So you just say it's the set of bilinear maps and that's it. Here it's a bit more involved. Okay, so this concludes the lesson for today. And I'll see you next week when we will resume this just general algebra things. And the next one we'll talk about is direct limits.
Yeah, okay. Well,